Hey everybody, welcome to Off-Nominal as seated on X. You saw it first on X, so welcome to the show.
I was pretty sure, like the rest of this drama, we were going to ignore it entirely, Jake.
No. I was going to see if I could break a record for how fast we talked about something weird that happened on Twitter. So it's we're going to go for it. We got Dr. Phil Metzger with us today, who's going to teach us about what rockets do to moon dust. I think is the ultimate objective from this, but we're going to do some pretty interesting thought experiments and talk about some of the cool experiments doing. Phil, welcome to the show. We're excited to have you.
Hi, glad to be here.
So we want to start. Do you want to start some drinks first? We've got some stuff. I got some fun stuff going on here. Anthony, you want to start us off, maybe? Yeah.
Sure. It's an old steady, Jake.
Okay.
Take a guess. Which brewery?
Yards, Pale Ale. I don't know I forget what the one.
It's a perpetual IPA, but maybe
Trogs.
Can I? Much like moon dust shot by rocket plumes, it is perpetual. Is that a fair tie-in? I'm trying hard. I don't get space beers out here, Phil. So it turns out the space beer market in Philadelphia not very big. So I have to just come up with these contortions to try to match Jake, who is currently in the Pacific Northwest-ish. But you were at least nearby enough that there's some beer.
Yeah.
Well, I'm just saying ish. Beer, yeah. It's closer than you've been. It's better than the beer company.
Yes, definitely closer than the other.
Yeah. What do you got?
Yeah. So I'm in Alberta right now, and yesterday I got my dinosaur on, and I drove up to the Royal Tyrrell Museum of Paleontology, which I haven't been to since I was a pre-adult, since I was just a little kid, and I used to go to Dinosaur Country Science Camp out there. I don't know. This might surprise you, Anthony, but I like to dig up rocks when I was a kid. Yeah.
I don't know if I've heard 4 words that better describe Jake Robbins. Well.
Yeah. So they have a craft brewery out there in Drumheller, Alberta now, and so I picked up this sweet Mesozoic West Coast Pale Ale. Is that Pacific and Northwest enough? I don't know. Maybe.
Jake,
it's got a Parasaurolophus.
What? Sorry, I'm stuck on you because I was pulling up something on the side here. Do you know what kind of dinosaur that is?
Yeah, it's a Parasaurolophus.
Oh, is it? Okay.
Yeah.
I didn't.
Trent.
Oh, nice. Oh, it's the one with the back part, right? The one with the back part.
Yeah, it's like a little horn kind of looking. I don't know.
I couldn't see when you're holding it up at first. I thought it was the one that was discovered out here in Haddonfield, New Jersey.
No, I don't think so.
Hadrosaurus.
Anyway, yeah. So Drumheller Valley Brewing, check it out.
Phil, I saw you were sneaking something pre-show.
I saw something.
You were getting busy.
There, yeah.
You were getting busy. What do you got down there?
Yeah, well, I don't have a great space tie-in, but it was the best I could get. This is, we'll call it a photon torpedo IPA.
I love that. That's great.
Wow. Are we all drinking IPAs today? Did we really just we really like white guy craft brewery it up today, didn't
Nailed it. Crushed it. One's got a dinosaur.
Yeah.
That's great.
Excellent. Okay, good.
So good.
So I don't know, where should we start? So Phil, maybe do you want to just tell us a little bit? So we brought you on because, I know you've been working on this stuff for a long time, but we were looking for a good excuse to tie it into current events. And we sort of got that by accident this year. But maybe you want to just tell us a little bit about the work you do studying. I'll see if I can characterize it right. Is it plume regolith interactions? Is that a good description for it? What's the situation?
The international sign for plume regolith interactions.
Plume regolith interaction, yeah.
When there's finally signs for landing zones on the moon, that will be the road sign. It'll just be two L shapes, you know.
Yeah. So tell us what you do.
All right. So I this topic was my entry into being a researcher. This is what I did for the first part of my doctoral research. And I've been working on this for about 25 years. Originally, I was asked by NASA to study this because we were going to build a refueling station on Mars for human-tended Mars missions. And we wanted to know, how do you land next to the landing pad without blasting your spacecraft? without blasting the refueling station. And so we had to come up with a way to protect the refueling station. So I started researching it, reviewing the literature, and I quickly found out that we don't even know the physics about how this happens. We don't understand almost not even the first thing about how rocket exhaust blows soil. And you might think, well, it's just gas blowing dirt. How complicated can that be? But the interaction of gas with a granular material invokes a lot of bulk behaviors that are hard to predict, like when you get bearing capacity failure, when you get fluidization of the soil, diffused gas eruption. There's a whole lot of phenomena like that.
I'm right there with you on all that. Yeah, totally.
Yeah, so we can't predict those things yet. Eventually, we got told we're not going to Mars, we're going to the moon. And so when you try to figure it out for the moon, it's actually even harder because now you're now blowing into a pure vacuum, or essentially a pure vacuum. And so the rocket exhaust, as it expands into vacuum, it becomes very rarefied. The mean free path length of the gas molecules gets so large that you can't have turbulent eddies of certain sizes, which gets larger and larger. And so it affects the turbulence spectrum, it affects the boundary layer flow. And so how it lifts the particles from the surface into the gas really cannot be quantified. And so we've spent the last 20 years doing experiments, simulations, analysis of planetary landing data, and trying to piece the story together. So we're pretty close to having some of the main pieces finished. I'm right now writing a paper where I think we finally got one of the big pieces figured out. But as you mentioned at the start of this, we just got to see the largest rocket exhaust cratering experiment in human history by far. I've never seen such a big gas jet blowing a hole in dirt before. And so we're trying to leverage that because that presses into the parameter space in a region we've never previously accessed. So I'm hoping we're going to get good science out of it.
Before we get to that one in particular, my main question is that there are several areas in spaceflight generally that I feel like are talked about as like existential threats, like radiation on long distance space travel, orbital debris. And like, if you're a nerd about this thing, it's like the existential threat is coming with that. And I feel like the plume-regolith interaction is talked about in a similar way because we have like pictures of surveyors getting blasted apart by Apollo landers. And there was was it NASA tipping point contracts a couple years ago for the, I'm going to forget the name. Wasn't it called like FAST or something, where they would inject like landing pad hardenization stuff into the plume? Like, there's all this work going on because if we can't figure out how to land near stuff on the moon, we can't really do anything interesting that requires like building up infrastructure on the moon. And it's talked about in an existential way. Do you feel like that is fair or unfair, or are you like, I don't really care, I'm just trying to figure out how dust works first?
Well, no, I've been involved in the applications, the policy issues as well. We've even had discussions with the White House, and we wrote a document at NASA some years ago talking about, well, it was recommendations. I'll just tell you the story about how that came about. But I got a phone call one day from Astrobotic Technologies, and this was during the Google Lunar X Prize back around 2010 or something. And they said, we want to land near one of the Apollo sites, but we don't want to damage the Apollo site, so tell us how to do it. And I said, well, okay, before I do, let me check with my management to make sure that I'm allowed to. And they said, absolutely not. You are not allowed to give them any information on this because we don't own the moon. We can't control what people do on the moon. And we don't want it to go to the United Nations because there's no telling what's going to come out if it goes to the United Nations. So do not discuss. And so I was biting my fingernails for like 2 years. Like, oh man, they're going to land and destroy the Apollo site. Not just about one company, but all the companies were talking about it. And I got this idea, okay, what we need to do is not create rules because we don't have the authority to create rules. Let's at least just create a document that tells people the best practices, and we will offer it as voluntary guidelines. And we will trust that no company wants to get the reputation of destroying the Apollo site. And so, and I mean, most of these people, I know these people in all these companies, and they're all very idealistic. So, I mean, they don't want to, but they want to know best practice. And so I was trying to figure out, how do we talk to NASA headquarters to get them to buy into this plan? And then I was going to do a reduced gravity flight where we were going to be measuring rocket exhaust blowing dust in low gravity. And this is the small version, the little micro experiment.
That's your G flight, yeah.
Yeah.
Well, with the curls, that means atmosphere, doesn't it?
Yeah. It rotates.
That's the Mars one.
Yeah. And it just so happens I didn't have enough money to pay for my 2 flight team members to go on the trip. And I got a phone call from somebody who said she wanted to know if her husband could go because he needed low gravity training. And I was like, absolutely, yes. And then she called back the next day and said, my husband's best friend would also like to go. He's at NASA headquarters and he can pay his own way. And when she told me the name of the guy, it was the exact person I needed to talk to about this problem. And I was like, heck yeah. So
zero G networking. Love it. Yeah.
That's right.
And you asked him the important question as you were pulling positive G's on the way back up. So he's like, yeah, sure.
No, I actually waited until after the flight was all done on one of the 4 flight days. And we went to a taco bar. And when we were at the taco bar, I'm like, okay, now's the moment. So I brought it up and he's like, absolutely. Yeah, let's do this. And so they put a team together, and it took us a couple of years, but we wrote the guidelines about how to protect the Apollo sites. And we had meetings with industry, and it finally got published. But then Congress passed a law that referred to that document. So I'm not totally sure, but I believe the FAA, whenever they give a launch license to do a lunar mission, they are going to check the box that, yes, this company intends to comply with the document. So it ended up becoming a rule, even though we just meant it to be a voluntary guideline. But so for a lot of years now, I've been working on policy issues related to this.
Okay. All right. So just to summarize then, so like, how bad of a problem is this? Like, is this something that we should be talking about a lot more, or are we talking about it just the right amount, or is this whole show just superfluous and we should be moving on to more important things?
No, I really do believe it's very important. So the ground truth on this was Surveyor 3, which you mentioned a minute ago. Apollo 12 landed 160 meters away from Surveyor 3. Yeah,
Is this the dock? Yeah, okay, cool.
That is.
And there's a picture of what we're talking about, which is perfect.
Yeah, so that's Apollo 12 lunar module on the rim of Surveyor Crater, 160 miles away. But you'll notice, this is not an illusion, the Surveyor is down in the crater and the Apollo LEM is up on the rim. And so we finally, after a lot of research, figured out that most of the blast ejecta blew harmlessly over the Surveyor. And it only got about 1/1000th of the damage that it would have received. So it was a 3 orders of magnitude reduction in damage. Nevertheless, the amount of damage was really bad. And so I have tried to extrapolate from that. Like, if you say, let's go to a 40-ton lander, and let's say that we need to get the damage to just 1% of the Surveyor damage, and we're going to land 20 times at an outpost. So 1/20th of a percent is what we're aiming for. How far away do you need to land? And the answer is 26 kilometers. And 26 kilometers is too far. You can't rove 26 kilometers. So
if I bike that far, I'm like, that was a good day on the bike. I did great. Like, it's all good. It's a good workout.
But in a spacesuit on the moon,
that's what I mean. Over craters. And, Well, at that point, 26 kilometers is like, it'll probably get blocked by some piece of crater or something. Like, it's so far that it's to the point of completely useless, which is exactly the point. Yeah.
Yeah. So we need to find a way to mitigate. use the natural terrain to block the blast, build landing pads. You could simply harden the assets, put screens and close your optics windows before landing. So there's things you can do, but probably some combination of all these different mitigation approaches. But we still don't know. I have a pretty good idea of the erosion rate now. That's the paper I'm writing right now. So we think we know the erosion rate, but we don't know how fast the particles blow. How they get lifted through the boundary layer and accelerated it's a very sensitive part of the physics. So if they get lifted faster, they go faster. If they get lifted slower, they go a lot slower. And so the different studies that try to predict these velocities all disagree with each other by really an order of magnitude. So they're saying between 200 to 3,000 meters per second. So that's over a factor of 10 disagreement. And the damage is going to be proportional to the velocity squared. So we're talking about more than 2 orders of magnitude disagreement in the amount of damage it will cause. And so we need to finish nailing this physics down. And already we're working on different methods to mitigate it.
Okay. Yeah. There's a lot to think about with that.
Yeah. Because it's also a weird like cold start problem of we have to figure this out, but like which thing do we do first? Do we just land some stuff on the moon again and try to characterize it as best as possible? Do we land 2 things near each other as an experiment? Like, should a follow-up CLIPS mission on a dead lander be land right next to it and see what happens? Like, is that a useful CLIPS mission? No payloads, just go land right next to the thing. It's probably worth tens of millions of dollars. Useful. Like, that would be a good $60 million task order, That's my proposal is the next 3 new CLIPS landers get no payloads. They just have to land successfully next to a dead CLIPS lander. That's the Anthony mission. So.
There you go.
Okay.
We'll put Phil in charge of it. It'll be great.
Yeah.
And as long as we get a position on the project team, we're good. So
yeah.
Or like a sticker on the lander. We're fine with that too.
We can
Googly
live
eyes.
stream the landing.
There's an effort to get googly eyes on an unnamed CLIPS lander. And I think we should support this movement.
Yes.
One time, speaking of googly eyes, I went to the Mojave for some flight tests on a rocket, and the guy that I had preparing our sensor that was the payload stuck a statue of a cat shooting a laser gun on our sensor, and I unpacked it and I'm like, ha, look. And the guys that ran the rocket program out there, they're like, oh, that is definitely flying.
Amazing.
They wanted that. Yeah, they wanted that to be on the payload when we flew it.
All right.
So good.
Cats with lasers and googly eyes. All right.
Mm-hmm.
Okay. Mm-hmm. Okay. So then let's. Okay. So we have this problem that we don't really well understand yet. So let's talk now about how we can tackle that. And I don't know. I guess did you watch the Starship launch live? And did you? When did the idea come to you? Like, oh snap! Like this is a useful thing. I need to get on this. I want to kind of hear the genesis of just watching a rocket launch like any other rocket launch to I have to science the shit out of this. Like, what's the through line there?
So I don't think I watched it live. I think I had some conflict and I couldn't. But I watched it on I think it was on Spaceflight Now. As soon as I could, and they started saying, "Oh man, there's sand falling down out of the sky," and as soon as they said that, I was like, "Oh my word!" They're like, they're 6 miles from the launch pad. Like if you took a shotgun filled with sand and shot it, sand doesn't go that far in air. It's going to stop because of the atmospheric drag, and it might go 100 yards at the most. A lot less than a bullet. A bullet will go a lot farther than a grain of sand. And so when it started falling down on them from 6 miles away, I thought, my word, what could possibly do that? So I put out a request on Twitter. Yeah, I recognize that. That plot is from the Mars Design Reference Mission 5.0 that was studying how far do sand grains go on Mars from a big giant, like a 40 ton rocket, which 40 tons in Martian gravity is a lot less than Starship in Earth gravity. But see, that distance is in meters, and the thing that goes the farthest, just over 700 meters, is pea gravel. So like 3 millimeters in diameter. It turns out that's the size that goes the farthest on Mars. And the thing is, bigger rocks, they don't get up to as high of a velocity because they're inertia. So they never get up to as high as a velocity in the first place. Dust will get all the way up to the speed of the rocket exhaust. So it goes even higher than the pea gravel. But as soon as it hits the ambient atmosphere, it screeches to a stop. And you can see those lines that go straight down on the left side of the curve. Those are the tiny dust-sized particles. They fly up at high velocity, but as soon as they lose their speed, they fall straight down. The ones that go the farthest are the pea gravel, like 3 millimeters. And they only go 700 meters. Now, in Earth atmosphere, there's a lot more drag. So the thing that's going to go the farthest is actually going to be even bigger, like big gravel or maybe even fist-sized rocks would go the farthest. And so there's no way anything should have gone 6 miles, certainly not sand, at least in my previous understanding. So I put out a call on Twitter and said, hey, anybody want to take part in a citizen science project?
If there's anywhere in the world that is like ready to do the most bizarre scavenger hunt in the world, is there anywhere better than Boca Chica? Like, come on.
Yeah. So we got great samples too. We got responses from like about 4 people, and we got more responses from people who shared their videos and their photographs, which are very helpful because it provides context. But one of the responses we got was from a lady who works at a bar on the beach. So one of her patrons collected samples at the bar and then told the lady, the barkeeper, about it. And she's like, oh, I'm in on this too. So she also sent me some samples. And so we're going to send a letter of thanks, certificate of participation. And we're going to include everybody as co-authors on the paper when we finally get around to publishing it.
That's awesome.
And we're going to mail their samples back, because they all wanted their samples back. I guess it's historic samples. And I would want them back too. But we not only got these sand samples, but we got a piece of the fondag, and we got a piece of another kind of material which looks like limestone. We think it was the underlayer beneath the fondag. And we got some other pieces that are just ordinary concrete. So there was a lot of stuff, different materials blown out onto the beach, and we got samples of all of those.
Get like a piece of an ocelot leg as well, or anything like that? No, nothing like that.
Bag of piping clovers.
Yeah, baby turtle.
I was really surprised to see limestone. I don't know the geology of that area, but I really didn't expect to get a piece of limestone. But I found out that limestone is often used as an underneath layer on concrete construction. So that's probably what it was. One of the coolest things was, so I've got a graduate student who's doing all this hands-on research. And he did visible and infrared spectrometry of all these materials. So we could try to identify the sand-sized particles, were they was it fondag? Was it concrete? What was it? And what he did was he brushed sand. There was sand stuck onto the limestone, and we brushed it off. And we found out that the sand that landed in Port Isabel, 6 miles away, is the same stuff as the sand that was stuck on the limestone. And so if the limestone was under the fondag and the sand was stuck on the limestone, that means this is the sand that was underneath the launch pad. And indeed, when you look at the pictures of the event, there's a big giant crater underneath the launch mount. And that crater... it's hard to get a sense of scale, but it's like, there you go. That crater is like 1 or 2 stories in height.
Yeah, it's big.
It's big.
Half of my house would fit in that. Like,
yeah.
I in the office I sit on would be at like ground level.
Well, are those on the left there inside the support for the mount? Is that a stairwell going up there?
Oh, where'd it go?
That's your sense of scale.
In
Aren't
here?
those
Yeah.
handrails for
Yeah,
stairs? Yeah.
yeah. There you go.
That's
Yeah.
that's
So
unreal.
each of those squares on that is a story. So you're talking about 1 or 2 stories deep in the center of that crater. Um, and also, by the way, you can see rebar cutting across between the two launch legs. That they didn't just put rebar in air like that. That rebar was inside concrete, and the concrete is gone, and the rebar is still there. So that stuff that used to be in all around the rebar is what they picked up on the beach. So this is like mind-blowing levels of physics right here. Like I've done a lot of experiments over the last 25 years firing rockets into dirt. I mean, hundreds. I've done 400 reduced gravity flight parabolas, or 450, and I've done many hot fire rockets and cold gas experiments. But the biggest crater I've ever seen before this was about 50 centimeters deep, half a meter. So this exceeds everything far beyond, this is pushing the experiments to a new part of the parameter space. But see that stuff in the bottom that you see down there, that's probably the material that rained down in Port Isabel. It was the sand that was under the concrete.
Huh.
And so, are you, like you were saying how you're not expecting grains to go very far, but and that's what you're trying to figure out is like, how did this turn into a cloud and drift? Like, what's I have no idea like where you're even beginning with then changing, a model to figure out how, if enough sand, then it might do this other thing.
Yeah, well, so one thing it gives us is a demonstration of how launch pads can fail. And we're really worried about launch pads failing on the moon. We've seen a launch pad fail once before. In Hawaii, the Pacific Islands Space Center for Exploration Systems, which spells Pisces.
Man, I was typing with you half the way there, but...
So Pisces built a simulated lunar landing pad where they took centered simulated lunar soil that was made into pavers. They were interlocking pavers, so they were supposed to hold each other down. And they used a robot to autonomously build the landing pad. Then they took a small rocket thruster, 100-pound thrust. And it was like, that wide of a rocket thruster on a paver that wide. So, it was a little tiny thruster right in the middle of a big paver.
Your hands weren't fitting on the screen, I noticed. So here, if you need to gesticulate,
here's the paver, and there's the rocket thruster. But what happened was the thruster cracked the paver. The thermal expansion cracked it. Just a crack, just a crack. But when you have 100 pounds thrust on 1 square inch, that's 100 psi. It pushes the gas through the crack, and it starts to build up the pressure under the pad. And the pressure will equalize to 100 psi. Well, 100 psi over 1 square inch is 100 pounds down. But 100 psi over 1,000 square inches is 100,000 pounds, right? 100,000 pounds pushing up. And so the whole launch pad just blew apart. And so we saw this once before. We thought, oh man, this is a bad failure mode. You don't want to be landing on the moon and have your whole launch pad explode, because then you got chunks of concrete hitting your rocket as you're trying to come down. You're not getting the heck out of there like Starship was. You're trying to come down into this mess. And so this gives us some more insight into launch pad failure now that we've seen how it can dig a crater underneath it. But the other part of it is, how did the particles get accelerated to such a high velocity that they could go 6 miles? And we still haven't finished that part of the research. So just like you showed that plot of the Mars Design Reference Mission, we're doing those same calculations for sand in Earth's atmosphere. By the way, we did measure the sizes and the shapes of those particles from Port Isabel. So we put them under a microscope, and we used software to draw little little outline of each sand grain, and then tell us the diameters and all the shape parameters, like the ellipticity and the surface area, the circumference to diameter ratio. So we've got a pretty good model of these sand grains. Most of them were about 100 to 300 microns, so it's like ordinary sand size particles. There were a few down in the 10 micron to below 10 micron range. The ones that are below 10 microns, those would be a breathing hazard. However, there were so few of them, it was way like a billion times below the hazard level. So it was really no hazard to anybody. But we did calibrate that, and so now we're going to try to find out how they could travel so far. Several people contact me through Twitter to point out that we get dust clouds from the Sahara crossing the Atlantic all the time. But see, that's a little different because those dust-sized particles are so small that the turbulence in the atmosphere keeps them suspended so they never fall down. And that's how they can travel long, long distances.
Yeah, it's not a ballistic trajectory, right?
Yeah, they also
right.
That would be the weird.
Right.
They also didn't start out at 3,000 meters a second or whatever. They started out at like wind speed, like fast wind, but not a rocket launch.
Right. But sand-sized particles don't blow over from the Sahara. Only the dust-sized particles do. So that's what made it surprising to see sand-sized particles landing in Port Isabel. So other people pointed out a really interesting analogy that, let's say when Mount St. Helens, for example, when it exploded, they did get sand-sized particles falling like 200 miles away. And so the difference there is when there's a volcanic explosion, it's a gigantic upward convection with such a giant mass of air that it continues upward for a long distance. And so that carries the sand particles up. And so then the crosswind can carry them a long distance as they fall back down again. So they don't get suspended like dust, but the upward convection carries them so high that they're able to get a lot of downrange travel.
More of a glider than akin to this situation.
Yeah, but that's what we're thinking happened. We're thinking that the launch pad failure was like an explosion, which created such an upward convection that it gave the sand a starting altitude that was higher than we would normally expect.
Your best analogy is Mount St. Helens. That's the thing we're saying is most akin to Starship's first test flight. Amazing.
Yeah, it is kind of amazing.
We just needed Jake on the beach saying Vancouver.
Vancouver,
and then we would be complete.
Oh
wow.
My goodness. Okay.
Yeah. So here's where I want to take this forward looking, right? We know Starship's general outline for what it would hope to accomplish. If you talk to anyone working on Starship, they would have a list of things they hope to accomplish. Many of those involve landing on other planets, right? And I'm using planets here, given our history of these three individuals saying that planets are everything, 'cause planets are great. Is it better or worse in the long-term view, 10,000-year view, that SpaceX blew up a launch pad in 2023? Because I feel like I'm coming down on the sides of, well, if Phil can figure this thing out based on blowing up a launch pad, then they've got a better shot of doing more interesting things on planets in the near future than if they didn't.
Yeah, so that's a great question. So there are two different approaches to doing engineering. One approach
So he's so nice, Jake. This is one of the nicest people we've ever had on the show.
Yeah, so one approach is you analyze the crap out of it and you spend 20 years analyzing it, and then it works perfectly on the first attempt, right? And there are times where that's the way you got to do it. Like, you don't want to build the Hoover Dam and like, oh, rats, the first one busted and we killed everybody downstream.
Yeah. At least we know now what happens when a dam breaks. Yeah,
that's
not a sentence we would say.
Hey, guys, be happy. We learned from it, right?
We got it.
But, the other approach is I really believe in it. This is the best way to do engineering when you can, and that is to fail early, fail often, but fail forward. So that you flush out the problems early in the program, and then as you continue through the systems engineering process, you get much more mature requirements, and you end up with a better product. So there have been studies that show that this approach does save money. I'm sorry, there's a dog barking in the background. Anyways, that approach does save money. And so I think it's a really good way to do things when you can. You can't always do that. Now, having said that, I do think Elon probably made a mistake in taking that risk on the first Starship launch, because it could have gone a lot worse than it did. If they had chunks of concrete hitting the rocket nozzles, and if they had a explosive engine failure, it's possible they could have lost the whole launch vehicle.
I feel like maybe those don't need to be ifs. I feel like isn't that the leading theory on what happened to at least the first couple engine failures?
Yeah, I don't know. I've heard people speculate about it, but.
You've heard people speculate about Starship? I'm surprised. I'm so surprised.
And is it the same people that sweep up sand to mail to you? Like, what's the crossover there?
Yeah. So there was a launch that failed out of the Vandenberg Air Force Base once. I don't remember which launch it was, but it failed not too high off the launch pad, and it basically leveled the whole infrastructure at the launch pad. And so that would have been bad. That would have set them back significantly more than it did. So I think they dodged a bullet. I think they got lucky, but nevertheless, they learned a lot. And in general terms, I appreciate the approach they use. I think it's generally a good approach.
Okay. I had a question, and now I'm trying to remember what it was, and all I can think about is sand.
Insert the Attack of the Clones memes here.
Okay, yeah. So I'm curious to know, so you're describing this problem where the engine shoots the exhaust through a crack, and then it pressurizes underneath it, and then it all blows up. So is this new plan then with this, like, they're building this huge water deluge system, which is like, I guess it's like a flat thing of steel that's got piping in it, and it's gonna that should. Well, actually, I'm asking if that's going to, save us from cracks. I assume that
is
metal
this the next thing that people will sweep up and mail you, or is it not? Is what Jake's question is.
Yeah, this is stainless steel 306 or whatever. Yeah, definitely these sand particles here. But like, does metal crack in the same way under the same pressures, or is this does this sound like a good approach?
Yeah, I think it's a really good approach. The big difference is that metal is a ductile material, which is the opposite of a I suddenly forgot the word.
You could literally say anything, and Jake and I will be like,
yeah.
Got it.
Well, a material that's brittle, a brittle material. So it's ductile instead of brittle. So concrete is a brittle material, and it fractures. Steel will bend and stretch because it's ductile. So the issue with steel is, are you going to melt it? And that is a concern. You could melt it.
The melting question people have asked for many years, in fact. It's been like 22 years since I've heard that question asked a lot. Yeah. Yeah. Yep.
Does Starship melt?
We're doing 9/11 jokes apparently today. It's been, yeah.
Would you get the same problem though then? Like if you melted a hole through it, would it pressurize underneath it and then blow the whole plate up?
Or let me try and possible. See if I'm right or not. We're doing this like full-on classroom thing. Wouldn't you have to melt the whole thing though, then, Jake?
So that's right. The thing is that heat travels through steel really fast. And so you're not just going to locally heat one part of the steel and get a burn through. The whole thing is going to be heating up. It will be locally a little bit hotter directly under the plume, of course. But the heat does transport through the steel at a pretty significant rate. So I was involved in a project at NASA called Morpheus. Morpheus was a small lander, like a lunar lander, where it was a test bed for testing systems for going to the moon. And they did a series of tests out at the Cape, and we were going to fly into this. We called it the hazard field. My group at NASA built the hazard field. I mean, we were out there with gloves, carrying chunks of concrete, stacking them up to build simulated boulders.
Is that
It
at
was
the
not
end
a-
of the shuttle runway?
It is.
Yeah,
Yeah.
this came up recently, Jake, on the show.
Yeah.
Yeah.
Yeah, so I was in charge of designing that hazard field right there. I mean, sort of. The Jet Propulsion Lab designed where the craters go, where the boulders go, and they told us every boulder in there, we want a boulder right here, this big. And they had it all figured out. And so it was my job to figure out where are we going to get these materials and build this thing. And so we had a bunch of interns, poor college students, out there in the hot Florida sun, and a front end loader. What we did was we got concrete rubble from a landfill.
I was gonna say first they had to find rocks in Florida, then
yeah, and there
After
aren't any. So we got demolished buildings, concrete, and we from a landfill, and a front end loader dumped it off, and then we would haul these chunks and stack them up. And so we built this thing, but the vehicle pops up in the air just like we just saw in the video. It has a LiDAR that maps the terrain, and it tries to identify somewhere safe to land. Once it identifies the safe place, it flies inertially to that location and then lands on it autonomously. Everything was autonomous. And we actually hid launch pads under the dirt because we didn't want it digging deep holes in the dirt and shooting rocks up at the vehicle. So we had buried launch pads underneath the dirt in the two best landing areas. But what happened was on one of those launches, it was on the launch of the vehicle, it took off and then it slowly turned upside down and drove itself into the ground and exploded. And what they figured
the old
out...
proton. Yeah. Protoned it up.
Yeah, so what they found out was that probably, we'll never know for sure, but probably, is this the video of that?
All right, this is number 8. Do you remember what flight number it was? I mean, it was probably the last.
I
can
don't
just look
remember.
up what the last one was.
I think it was actually before all of the successful ones.
Oh, okay, good.
I think. But anyways, they...
You built a weird vehicle. If it crashed itself into the ground and all the success was after that, that was a weird vehicle. If it's the same one.
It was the second build. They built a new one.
Mark II.
Yeah, but that was actually an Armadillo Pixel, which NASA procured from Armadillo Aerospace and then modified it. But anyways, what they found out was that the noise, the rocket noise of launching shook the vehicle so much that probably a connector came loose. And it was the connector that carries the rate gyro information back to the computer. So it's like, the inner ear, you've got those little things that tell you which way you're turning your body so you can tell which way it's up or down. It's like you lost that. Oh, there we go. That's it. Yeah.
That's a good one.
That was the event. Yeah, we were all like, oh, rats, when that happened. So after that happened, we figured out it was probably the rate gyro because of launch acoustics, and we need to mitigate the launch acoustics. We also need to connect that connector better next time, but we need to try to mitigate the launch acoustics. And so we decided to build a flame trench, and we made it out of steel. And so we took a backhoe. Yeah, so we took a backhoe and we cut the cement, and then we dug and then dropped in this steel flame trench. And I did the thermal analysis to decide will it melt or not. And what I found was that it was big enough that even if all the heat of the plume went into it, it still would not melt. But being NASA, the old saying is that NASA engineers wear belts and suspenders. We decided we're also going to paint ablative material all over it. And it was like a white silicone material like you might paint on the roof of a building. And so the silicone, it breaks down under heat, and that uses up the heat. so that the amount of thermal energy is reduced as you're ablating the silicone. So we
Right.
painted that all over the steel as a secondary way of protecting it. And then it was successful. We flew on those on those cement assets multiple times and had no problems with it.
All right. Okay, so talking about the moon then, so this is obviously an issue that both SpaceX and Blue Origin are going to have to figure out. We cannot install cool flame trenches or steel plates at least on the first few landing pads that we use on the moon. We've seen, I guess Starship is thinking about engines up on the top, on the sides, kind of, away from the ground. I don't know if Blue Origin has a publicly announced mitigation strategy for that, but what are you hearing about that? And what is maybe just generally are they is the lander of that size going to pose a pretty significant problem for going down on the moon? Because it's obviously something they got to figure out if true, right?
Yeah, so I have to be careful because I have a non-disclosure agreement. I did some work. I did some work for them, but I'm allowed to talk about anything that's publicly known.
Sure.
So in general terms, heck yeah, it's a problem if you have a 150-ton vehicle or whatever it is landing on the moon. The Apollo lunar module was 7.5 tons, and so if we're talking about, I don't know what it's going to be, but if it's going to be 150 tons, then that is so big that it could potentially create a giant hole in the ground, and then that could cause failure of the vehicle and damage lunar assets that are nearby. The ejecta even goes to orbital altitudes. So if you have a vehicle in low lunar orbit that happens to come by at the wrong time, right in view of this ejecta shooting out, then it could sandblast the vehicle that's in orbit. And it's not going to destroy the vehicle in orbit, but it would be about 1% of the optics would be scuffed up, and I think 1% of a sensitive instrument is still pretty bad. So it's a big issue. Now they have put out these pictures showing these upper thrusters, and that is a really, really good approach. Upper thrusters dramatically reduce the ejecta that will blow from a vehicle. I mean, it's the same thing as when your vehicle is high. When your vehicle is high, the simulations show that the ejecta is a lot less, and it goes a lot slower. It doesn't get up to nearly the same velocity. So we're talking like, instead of 3,000 meters per second, we're talking like 50 meters per second.
Much better.
Yeah, instead of like 5 times the speed of a bullet, we're talking about 1/10 the speed of a bullet.
The only thing I can't figure out with these side thrusters, because that's like the first place I would go to, is get the engines higher up. But if we're on the moon and we've like ultimately you want your rocket engine to point down, because then you get to use all of the power of the thruster. But so one thing you could do is like kind of just tilt a little bit of a side to avoid thrusting into your own vehicle a little bit, right? And we've seen that, some sort of like kind of like, I don't know what you call that, just like angled thrusters.
Canted.
But sure. But in a vacuum,
nailing it, Jake. I'm getting the A in this course right here.
In a vacuum, your exhaust expands pretty significantly, and so is the Starship thruster on the side, even if it's tilted out 10 degrees, is that still not just going to soot up the side of the lander from halfway down? I'm trying to figure out how they're going to approach that, right?
Yeah. So normally when you have a rocket engine, the rocket exhaust comes down the inside of the nozzle, and then when it gets to the edge of the nozzle, it turns. And the amount that it turns is called the Prandtl angle. The Prandtl angle. So in lunar vacuum, it actually turns more than 180 degrees. So you are getting upward flow coming out of that nozzle. It comes out, and some of it goes up. So it does fill more than the whole hemisphere below the vehicle. However, because of conservation of momentum, most of it goes down. So when it hits the ground under the vehicle, you get a Gaussian distribution of pressure. So it's peaked up right like a bell curve. So it's peaked up, highest pressure is right in the middle, and then the tails of that Gaussian like cover the whole moon. It never goes to exactly zero, but it becomes insignificant.
Covers the whole moon.
Yeah.
That's amazing.
Well, I mean, really, if the ejecta goes 3,000 meters per second, escape velocity on the moon is, oh goodness, it's slipping my mind now. It's 1.4 kilometers per second, 1.6. So I know this number, but now that I'm on a live stream, I can't remember the number.
Yeah.
But anyways,
it's the opposite of ductal is what the answer is. Yeah.
Yeah, that's right. Yeah, that's right. So, but anyways, the ejecta goes far higher than lunar escape velocity.
Yeah.
Those are the fastest particles, but there are particles that go all speed from that to zero. And so there is, at every distance on the moon, there are particles that will go that distance. So the ejector literally blows over the entire global moon every time you have a large vehicle, like at least 7-ton vehicle, land on the moon. But fortunately, the flux becomes very low that far away. So it's at some distance, it becomes less than the natural flux of dust falling from space. And so beyond that distance, you don't really care anymore. But it is global.
But you're saying that because of the way that pressure is distributed, it wouldn't dig out the area where the lander's going to land by having the engines canted out in that way?
We don't really know.
Again,
so
we're just making it up until we do it.
Well, so on Apollo, it did not dig a hole. And the people that are skeptics that don't believe we landed on the moon, they always point that out, like, oh, there was no crater. Well, there was.
Because they've landed on the moon and they know how it would work if they put a rocket engine on the moon. Clearly, yeah.
Yeah, I mean, we predicted that it would not be a crater. Before they landed on the moon, they predicted it would be a gradual dip, and it would be a toroidal. It would be deepest in a toroid around the nozzle, not directly under the center. And that's what it was. About a meter away from the center of the nozzle, it was 6 centimeters deep. That's what we saw, and that's what we predict. So there was a crater. It's just a very broad, shallow crater. But you don't get this deep digging. We have a technical name for when the soil fails underneath the nozzle and it makes a big hole. We call it deep cratering. And so we did not have deep cratering on the Apollo mission. We only had scouring of the surface. But the deep cratering processes do occur. We see them in the experiments. You saw it on the Starship launch. And the thing is, we don't know the physics well enough to be able to predict where that transition occurs. So if the Starship is coming down, if it came down on its main engines, how high would it have to be, or how low would it have to be for the soil to fail and do deep cratering?
Right.
Nobody can predict that because we don't understand the physics.
All right, we'll do it the SpaceX way then. Just fly in there and see what happens.
Blow the moon up.
That's what the uncrewed landing is for. It's the deep cratering experiment. Okay, good.
So there's 2 CLIPS missions that you're in charge of, Phil. There's land right next to a dead CLIPS lander, and there's pick a spot on the moon where we should land a huge rocket engine and see what happens. And you don't have to answer that right now, but let me know at some point what part of the moon we should do that on. I would like to figure that out. Phil, number one, this has been by far the most educational episode of this podcast of all time, in the greatest way possible.
We've never had this many science words on this podcast.
No, we're doing great. We're killing it. We made a 9/11 joke even amongst that too. So we're firing on all cylinders here.
Yeah.
But are there things that you're working on day to day that people can or should follow along with? Because I was a Morpheus stan for a long time. I've always been intrigued by Morpheus. So I've been a Dr. Phil stan of this variety of Dr. Phil. The other one I don't really have an opinion on, little to no opinion on. But where should they follow along if they have not experienced you yet.
Okay, sure. So I am on X. I'm on the app previously known as Twitter. My Twitter handle is Dr. Phil Till. So DrPhilTill. My middle name is Tillman, so Phil Till. So you can find me there. I'm on Instagram. Same thing, Dr. Phil Till, but I don't do much on Instagram. But yeah, I try to interact. I try to reply to everybody who sheets at me, or however you pronounce it.
Amazing.
I'm going with the Chinese pronunciation.
I love that.
It's sheet.
Yeah.
So if you want to sheet at me, I will sheet back at you.
That's different than the Western Pennsylvania sheets as well. Slightly different thing. Yeah, that's totally.
It just is making a reminder. We need to talk to Michael Sheets about his account though, because then his new handle is now Sheets.
Yeah.
Sheets squared. We should change his handle. Yeah. He needs to change his handle to Sheets squared. Yeah. So. Oh dear. Okay.
This went places. Love that.
All right. Yeah, you do great sheet threads there. So it's nice to see some of the stuff that goes on there.
They're called piles of sheet.
Yeah.
This is great content. It's so good.
Check.
Yep, nailed it. And you're at UCF as well. Shout out to the school I didn't go to because I went to Full Sail on the other end of the boulevard there.
Oh, you went to Full Sail. Awesome.
I did. I'm one of those weirdos that bummed off the UCF library discounts for Apple software back in the day. So that was great. They felt sorry for us and they gave us the discount at the school bookstore so I could go in and buy discounted stuff. It was great.
Well, that's cool. That's really cool.
Between that and crashing UCF parties, that was mainly my experience of UCF while I was there. Yep. Pretty good.
Yep.
That's local Florida content for you, Jake. I hope you enjoy that. Yeah.
Yeah. I barely know where UCF is, so this is good. Yeah. I assume it's in the middle, just from context, but.
You would know where it is if I pointed it out on a map. You'd be like, "Oh, I've seen that." Yeah.
Would I?
You would. Yeah.
Okay.
I can say confidently we've been nearby it together.
Okay.
So, yeah.
So it's by the airport, is what you're telling me.
No, I just know where the route we drove. We were.
Okay. All right.
Yeah, we were close enough.
Okay.
Jake. Well.
Yeah.
What else we got?
What's going on next week? I don't think I'm around next week, Anthony. So
I'm gonna say TBD because I'm working on some scheduling.
Okay.
It's likely. It's gonna be a weird one, no matter what, Jake. Okay. But and it's likely gonna be some sort of matinee that would be more applicable to the European time zone.
Okay.
Or the whole thing will fall apart in the next day and a half, and we'll do something else.
All right.
So there we go. That's where we're at, and stay tuned. But if you're in the Off-Nominal Discord, you'll have the inside track on that.
Mm-hmm. Yeah,
so
head over to offnom.com/discord. You can join up for anywhere between $5 and $25 a month based on how much you like us. And
I don't know if it's anywhere in between. I think it's either $5 or $25.
It is a binary state. Yes. 5 or 25. So please help us out by supporting us, and then we can make more shows like this and get great guests like Dr. Phil Till on the show to talk about ductility of concrete. So yeah.
I was 85% sure the till was a nod to tilling soil.
Yeah, that's what I thought too.
I thought it was a pun. Yeah.
Yeah.
Wow, that's a good slant on it. Yeah.
Yeah. You were always destined for this job. You didn't even know it until right now. Yeah. Probably because he's not showing it, but he's really angry that I said soil, Jake. Furious. He's as mad as he gets.
What if his second middle name is Regolith, though? We were missing a very, very common, obvious.
He'll have to change his Twitter handle because of this, or his sheet handle, whatever we're going with. His sheets.
His flusher. That's what we call the sheet handle.
His call sheet. Oh, we should leave.
Dear.
We should get out of here.
This is over.
Phil, you're the greatest.
So much, Phil.
We love you. This is the best. Thank you so much for coming on.
Talking with you both. All right.
See you later.